Heat, specific latent heat of fusion of ice. So in 2008, question 2, this experiment came up. So in the experiment we were told that the student wanted to measure the specific latent heat of fusion of ice, not to be confused with vaporization of water. And we were told that warm water was placed in a copper calorimeter, and then that we had dried melting ice added to warm water, and the following data was recorded. The first thing to note is that we have our mass in grams, and those grams are going to have to be converted to kilograms. We're given the mass of the calorimeter, we're given the mass of the calorimeter and the water combined, we're given the temperature of warm water, we're given the mass of the ice, and we're given the temperature of water after adding the ice. So we're going to break down the question into parts. So we're going to say A, explain why warm water was used. B, why was dried melting ice used? So be careful, there are two words there. Why did we use dry ice and where did we use melting ice? C, we have to describe how the mass of ice was found. And D, we have to say what should be the approximate room temperature to minimize experimental error. And then E, we have to calculate two things. The first thing is the energy lost by the calorimeter and the warm water. And then 2, the specific latent heat of fusion of ice. And we're given our specific heat capacity of copper, and we're given the specific heat capacity of water. So that's going to be our specific heat capacity, small c, C for copper, and CW for water. And then F, we're asked what would be the approximate room temperature to minimize experimental error. Okay, so once we do each question, we can tick them off once we've marked them, because obviously in the Leaving Cert, they never have them labelled as 1, 2 or 3, only really for like little bits like here in the calculation. So it's better to tick them as we've done off each question so we don't miss one. So the first one is, why do we use warm water? Well, by using warm water, what one it will do is it speeds up the melting of the ice. It also allows us to add more ice. And if we melt a larger mass of ice, that means we're going to get a greater temperature change, which is easier to measure and reduces our percentage error. And one of the main things is obviously as well is to prevent heat loss and heat gain to the surrounding. Or heat gain. Because obviously if it gets too cold, then it's going to gain heat from its surroundings. So any of one of those would have done for an answer for 3 marks. So they're all acceptable answers in this case. So B then says, well, why did we use dry melting ice? So by drying the ice, is important because it removes any excess water. Before we add it into the calorimeter. And our calculations assume we are only adding ice. So if we didn't dry the ice, then that would affect our calculations and cause a larger percentage error. Now, why do we melt the ice then? again, the melting ice is used so that the temperature is at 0 degrees Celsius. And again, our calculations assume this. Because when we're looking at our temperature change for the ice, we always start at 0 to the final temperature. So if we are not adding ice that is melting, it is not at 0 degrees. It could be at lower than 0 degrees. And again, that would affect our experimental error. Okay, so C then says, well, describe how the mass of the ice was found. So that's a very easy one. The mass of our ice is equal to the mass of the calorimeter and water and ice, in other words, the final mass, minus the mass of the calorimeter and water. So by getting the difference between the two of those, we end up with the mass of ice. So it was 3 for talking about the drying the ice, and 4 for talking about the melting ice, or vice versa. And then describing how the mass of the ice was found was 6 marks. So D says, well, what should be the approximate room temperature to minimize experimental error? Now, if we look at this experiment, we can see the temperature of the warm water is starting at 30.5, and the temperature of the water after adding the ice is at 10. So normally we start with warm water just above room temperature, and we add enough ice to bring it down just below room temperature. So in other words, we want our value to be somewhere between the starting and the end point. So therefore we should expect the approximate room temperature to be halfway between 30.5 and 10.2. So in other words, the approximate room temperature is halfway between the start and the final. So it should just be halfway between those two values, which is, of course, halfway between 30 and 10 is 20 degrees Celsius, okay? And again, that was 6 marks. Okay, so the next thing we want to do is our calculations. So we're going to go on to the next page for this. And the first part of our calculation wants to look at the energy lost by the calorimeter and the warm water. So of course we know that we have heat loss is going to be equal to our heat gain. And what's losing the heat is our calorimeter and the water. And what's gaining the heat is the ice. So of course our heat loss from our calorimeter is going to be mc delta theta and mc delta theta, because there's a change in temperature, and that's going to be equal to ml for the ice. But of course the final temperature is at 10 degrees there, so there is still a change in temperature for the ice once it has melted also. So we're going to have the calorimeter, which we're told is made from copper, and then we have the water, and then we're going to have the ice, and ice is going to be fusion, and then mass of the ice, and of course when ice melts it turns into water, and the change temperature for the ice. So I is equal to our ice, W is equal to our water, and C is equal to our copper calorimeter. So we're only looking for the left-hand side of the equation here for the first part, and then we'll put the two together for the second part of the question. So our energy, our heat loss, is our mc delta theta for the copper. So our mass of our calorimeter is 60.5 grams, which has to be converted to kilograms. So we have 60.5 divided by 1,000 is equal to 0.0605. And that's by our specific heat capacity of our copper. And again, if we come back here, we can see that that is 390. And then the change in temperature for the copper. So of course the change in temperature is 30.5 minus 10.2. Again, that's our degrees Celsius. Plus the mass of the water. So to get the mass of the water, we saw that we have our calorimeter and our water. So the mass of the water is going to be the difference between the two of these. So to get our water, so it's going to be 118.8 minus our 60.5. And that'll be the mass of the water by our specific heat capacity of water. And again, in this particular question, it's given to us as 4,200. So a lot of the times in our books, we're using 4,180. So they've actually rounded it to two significant figures here for that particular year. So again, don't assume, always check what are they giving you each year. Could be subtly different. And again, our change in temperature, again, is 30.5 minus 10.2. Okay, so let's simplify that. So we have 0.0605 times 390 times 30.5 minus 10.2 gives us a value of 20.3 plus 118.8 minus 60.5 gives us our mass. Sorry, that actually should be in... I have to divide that by 1,000 to turn it into kilograms, so that's 0.0583. So let me just go back there and change that to kilograms, sorry. So that should be 0.1188 minus 0.0605 there in kilograms. Same here. And then that is times 4,200 times 20.3. Okay, so let's put all of that into our calculator. And then if we simplify that, that gives us 5,449. So 5,449.64, and that's joules. So we had 9 marks going for that. So again, 3 for our formula, 3 for our substitution, and 3 for our answer. And of course we lose 1 mark if we don't have our units correct. So the second part of the calculation then is to work out our L. So of course this is where we're going to sub it straight into this formula up here. So we're going to have our 5,449.64 is equal to the mass of our ice. So to get the mass of our ice, again, we need to go back and we can see our mass of our ice is 15.1, but that's in grams. So we need to divide 15.1 by 1,000, which gives us 0.0151. Times L, which is what I'm looking for, plus our mass of our ice, 0.151, times our specific heat capacity for water, which is 4,200, times the change in temperature for our ice. So again, ice starts at 0, and the final temperature is 10.2. So we have 10.2 minus 0 for our change in temperature. So now we want to rearrange to get L on its own. So we have 0.0151 L is equal to 5449.64 minus, if I bring everything over to the right, which is 646.884. And then if I subtract those, we end up with 4,802.756, and then divide across by 0.0151, and that gives us L is equal to 318,063.3113, or in other words, L is equal to 3.18 by 10 to the power of 5, and of course we can't forget our units is joules per kilogram. So again, we were getting 3 for our substitution into our correct formula, 3 for equating, and 3 for our answer. Okay. And then the last question then says, well, what should be the approximate room temperature to minimize experimental error? Sorry, I've just realised that last part there shouldn't be there. That's actually just doubled up. So we'll remove that. So any of your mandatory experiments, they're always 40 marks in total. So it should be taking you just 20 minutes approximately to answer these questions. Okay, so you're now going to go and you're going to do your virtual online lab experiment.